So the lecture today will be on reflexive spaces. So we have seen that if we have X, a normed linear space, we represent it by X prime, the space of bounded linear functionals over X. So this is the space of all L, which are functionals from X to K, which are bounded and linear. And this space X prime is normed, so we define the normed of L to be the supremum over all X with norm equal to 1 of L of X. So X prime is a normed linear space, and we could, in the same way as we defined the dual of X, define the dual of X prime. So I will represent by X prime prime the dual of X prime. So this means that X double prime is the set of all functionals L, and I will represent the elements of X double prime by capital L and the elements of X prime by small l in this lecture. So this is the set of all L from X prime to the field K, such that, well, L is linear and it's bounded. And as we did, we can define the norm of L as the supremum over all L in X prime, whose norm is equal to 1 of L of L. So we'll study today this space, which is a dual of the dual space of X. So let me start with an example. We have X, our normed linear space, X prime the dual, and X double prime the dual of the dual. Elements of X will be represented by X, Y, elements of X prime by L, eventually M, and elements of X double prime by capital L. So I want to give you an example of an element of X prime. So fix X in X and define the linear functional Lx on X prime to K, which to a bounded linear functional L on X, small l, gives Lx of L, which is L of X. So I claim that Lx is linear and bounded. And this is easy to check. So let's check. And then once I prove that it's linear and bounded, we will compute the norm of Lx. So to show that it's linear, we have to consider two elements. So alpha will be a scalar, and L and M will be elements of X prime, so bounded linear functional. So this defines a new bounded linear functional, and by definition, this is just alpha L plus M computed at X. But this, by definition of this linear functional, this is alpha of Lx plus M of X. And by definition of Lx, this is alpha Lx of L plus Lx of M. So we see that indeed Lx is linear. And now to show that it's bounded, well, let's compute the absolute value of Lx of L. So this is, by definition, L of X. Now, by definition of the norm of L, this is bounded by the norm of L multiplying the norm of X. So this proves that, so remember, the norm of L is the supremum over all L whose norm is equal to 1 of L of L. So now if I take here a linear functional L whose norm is equal to 1, this is equal to 1, and this means that this supremum, it's bounded by X. So this proves that Lx, the norm of Lx, it's bounded by the norm of X. And this proves, therefore, that this linear functional, it's indeed bounded. So we have defined a bounded linear functional by this formula. Lx of L, it's equal to Lx. Now I will erase the board and I will compute the norm. I will prove that actually what we have is that the norm of Lx, it's exactly equal to the norm of X. So I rewrote here the definition of the bounded linear function Lx, and we proved that this inequality holds. Now I want to say that actually it's an identity, and for this identity we need to remember a formula which we proved. We proved that the norm of X, it's actually equal to the supremum over all bounded linear functionals L whose norm is equal to 1 of Lx. So remember we proved that identity, but this by definition it's equal to the supremum over all L with norm equal to 1 of Lx, but Lx it's Lx of L, and this is exactly the norm of Lx. So we have the identity I claimed, and this means that we can actually think of X as a subset of X prime. So we can, we have a functional L from X to X prime, which associated to a vector X in X, the element Lx, and this is an isometry because we just proved that Lx is equal to X. Right? So in this sense, we are embedding through this functional, we are embedding X in X double prime. X can be considered as a subset of X double prime. And a natural question is, well, are there other elements in X double prime which are not in X? And this is the main topic of the lecture today. So definition, a space X, this is a normed linear space, will be said to be reflexive if X double prime is equal to X. So that's a definition, and well, let's start with some examples. So one first example, which you certainly learned in linear algebra, is that if X is a finite dimensional normed linear space, then it is reflexive, which means then X double prime is equal to X. And then a second example, which comes from measure theory, is that, well, assume that P is between 1 and plus infinity. Define Q as the conjugate of P. So Q is such that 1 over Q plus 1 over P is equal to 1. Consider a measurable space omega with a certain sigma algebra F and a measure mu. Take the space LP of omega, so this is the space, remember, of all functions f from omega, let's say to R, which are measurable with respect to the sigma algebra, and such that the integral over omega of f p d mu is finite. So we've seen that LP, it's a normed linear space. And, well, you've seen in measure theory that the dual of that space, it's exactly LQ. Okay. So maybe any linear functional L from LP of omega to R can be represented in terms of a functional of LQ. So L of f will be given by the integral over omega of fx gx d mu x. So what I claim is that if L it's a bounded linear functional in LP, then there exists a G in LQ such that L of f is given by this formula, and therefore that you can identify the dual of LP with LQ. Once you know that, you see that, well, if Q is the conjugate of P, P is the conjugate of Q, which means that if I consider the dual of the dual, I get the dual of LQ, and by the previous claim, this is just LP of omega, and we have an example in which the space coincides with its, the dual of its dual. So we have here an example of a normed linear space which is reflexive. So now let me give you an example of a space which is not reflexive. So let's represent by C minus 1, 1, the space of continuous functions from minus 1, the interval minus 1, 1 to R. And this space is endowed with the sup norm. So this means that for an element, for a continuous function, this norm, it's just the supremum for t in minus 1, 1 of x of t. And what I want to prove is that it's not, well, that this space is not reflexive. So my claim is that this space is not reflexive. So this is my claim. And the proof of this fact will be based on the following observation. So remember, if I have a space X and its dual X prime, I can represent L, and I used this fact before here. I'm sorry, I can represent the norm of X as a supremum of Lx, in which this supremum is taken over all linear functionals whose norm is equal to 1. And, well, what we proved actually is that this supremum is a maximum, so it's attained. So what we really proved is that there exists L0 such that the norm of x is equal to L0 of x. So to be precise, what we proved and what we'll be using here is that for any x in x, there exists a bounded linear function of L0 which has norm equal to 1 and such that the norm of x is equal to L0 of x. So this is what I'm going to use, but actually not to x and x prime, but I will use that for the space. Well, I won't be writing C minus 1, 1, okay? I'll just write C, C prime, and C double prime. So if I apply this result to the space C prime and C double prime, it tells me that for any L in C prime, there exists L in C double prime, the norm of L it's equal to 1, and the norm of small l it's equal to L. So this is just to apply an old result in this special case. So in order to prove that this space is not reflexive, I will assume by absurd that it is. So assume by contradiction that C it's equal to C double prime. And from this identity, I will obtain a contradiction. So if it's true that C it's equal to C double prime, it means that all element of C double prime is actually 1Lx. So in this statement in this case would state that whatever bounded linear functional L, I can find one element in C double prime, and since C double prime coincides with X with C, so I can find Lx whose norm is equal to 1 and such that the norm of L is equal to Lx of L. Well, but to say that we can find Lx in C double prime, it's the same as we can find X in C. We've seen that the norm of Lx is equal to 1. The norm of Lx is equal to the norm of X. So this means that dc has norm equal to 1. And Lx of L is L of X. So if we assume that C double prime it's equal, so if we assume that the space is reflexive, which means that C double prime is equal to C, what we have is that whatever bounded linear functional L defined on C, we can find a continuous function, x, which has norm equal to 1, and such that the norm of L is equal to Lx. So I will be using this result, and I will get a contradiction from this result, proving that C double prime cannot be equal to C. So I want to prove that this space C of continuous function is not reflexive. So I assume that it is. From that, I concluded that whatever bounded linear function L, I can find a continuous function which has norm equal to 1, and such that the norm of L is equal to Lx. So now I'll get a contradiction. And the contradiction will be obtained for a special bounded linear functional. So let's consider the following bounded linear functional L, which applied to G, it's equal to the integral from -1, 0 of G minus the integral from 0 to 1 of G. So it's clear that L, it's a bounded linear functional, right? Well, you can estimate this integral by 1 times the infinite norm of G plus 1 times the infinite norm of G. So what I claim, and it's clear that L is linear. So L is a bounded linear functional, and what I claim is that its norm it's equal to 2. Well, on the one hand, if you take L, if you want to estimate Lg, so you have the absolute value, it's clear that the absolute value is bounded by the sum of the two absolute value, and that each integral it's bounded by the L infinity norm of G times the size of the interval, which is 1. So it's clear that this is less or equal than 2 times G infinity. And from that, it follows that the norm of L is at most equal to 2. Now, we need an upper bound, a lower bound for Lg. So let me take a functional which is defined between a function, function defined from -1 to 1, I will fix an epsilon positive. I will consider the following function. So this function will be equal to 1 from -1 to minus epsilon. It will be equal to -1 from epsilon to 1, and say that it's linear in between. So this is my function g of epsilon. Well, the norm of g of epsilon, it's equal to 1. LG, sorry, the norm of L it's equal to the supremum over all functions f in C whose norm is equal to 1 of L of f. We have seen that our G epsilon has norm equal to 1, which means that this supremum, it's larger or equal than L G epsilon. And, well, it's clear from the definition of G epsilon, well, that this will give you a contribution of 1 minus epsilon 2 times. And then, well, there's a piece here which will give you a positive contribution and a positive contribution. So actually, LG of epsilon in absolute value, it's bounded below by 2 times 1 minus epsilon. And so from this inequality, we get that the norm of L, it's bounded below by 2 times 1 minus epsilon, and that for any epsilon, which proves our claim that the norm of L, it's equal to 2. So we just prove that the norm of this bounded linear functional, it's equal to 2. And now let's use what we proved before, is that, well, for that functional, we can find a continuous function x, which has norm equal to 1, and such that L of x, it's equal to 2. So now L of x, it's equal to this interval from -1 to 0 of xt dt minus the integral from 0 to 1 of xt dt. So x has infinity norm equal to 1. So this means that we have a function, continuous function, from -1 to 1, which is bounded above by 1, bounded below by -1, and we need to compute this integral. So I leave it to you to check that L of x, it's always strictly smaller than 2. You can't find a function, a continuous function xt, which takes values between -1 and 1, and for which this integral is larger or equal to 2. See that, well, you want it to be positive, so either, well, it takes a value which is smaller than 1 in a point. If it takes a value smaller than 1, well, the function is continuous. It will take a value smaller than 1 in an interval, and now you can't turn this expression equal to 2, because to get it equal to 2, you'll need a function to be 1 between -1 and 0, and -1 between 0 and 1. And if you want the function to be continuous, well, if it's 1 in this interval, at some point you have to cross, and you'll get an interval in which it's exactly comprised between -1, strictly larger than -1 and smaller than 1, and therefore you won't attain the value 2. So that gives you a contradiction, because, well, we have here a functional which has norm equal to 2, and whatever continuous function whose norm is equal to 1, the value of Lx, it's strictly smaller than 2. So there is no x continuous function for which this identity holds, and therefore you have a contradiction, and this proves that the space of continuous functions with the infinity norm is not reflexive. So here is a nice theorem. So let's consider X a norm linear space. And since I will use Hahn-Banach theorem, let's consider that the scalars are the real numbers. And let's assume that X prime is separable. So I just remember that separable means that there exists a dense countable subset of X prime. And what I claim is that in this case, X is also separable. Okay, so here's the proof. So we know that X prime is separable. This means that there exists a dense countable set. So let's represent this dense countable set by Ln. So this is dense in X prime. And to show that X is separable, we'll construct a space which is countable and dense in X. And for that, we will start by an observation that, well, has been used here many times. The norm of Ln, it's equal to the supremum over all elements z in X, which have norm equal to 1, of Lz. And, well, since this is a supremum, if I fix, I'm sorry, here's Ln, and since this is supremum, I can find one which almost attain. So I can guarantee the existence of Zn in X, which has norm equal to 1, because I'm taking a supremum over all such points, and such that Lnz, well, attains almost the supremum. So let's say that it's larger than 1/2 of the norm of Ln. And here the norm of the fact that it's 1/2 doesn't play any role. So we could have taken here any number smaller than 1. And, well, either this is positive or negative. So by changing Zn by a plus or minus 1, by a minus 1, eventually what we get that we have a point Zn which has norm equal to 1, and such that L of Zn, Ln of Zn, it's larger or equal than 1/2 of the norm of Zn. And my claim is the following. What I claim is that, well, if I consider the closed linear span of Zn, that this is equal to X. So this is the claim I will prove, and we will prove that, again, by contradiction. So I will suppose that it's different, and I will get a contradiction from that. So I will raise everything. I will start by this family Zn, and we will prove this claim by contradiction. So we wrote what we did up to now. So we have a family Ln which is dense in X prime, and then we constructed a family Zn of points in X. Zn has norm equal to 1, and Ln of Zn, it's bounded below by 1/2 of the norm of Ln. And my claim is that, while the closed linear span of this family, it's equal to X. I will assume by contradiction, so let me call Y the closed linear span of Zn. And let's assume that Y is different from X. So if Y is different from X, we can find a point X which doesn't belong to Y. And now, well, we did that many times. You could consider the space, the linear space of all elements which can be written as a scalar times X plus an element of Y. So Y alpha in R, Y in Y. and define a bounded linear function on this space, use Hahn-Banach to extend it to the whole space. Why it's a closed set? So it's possible, and we did that already before, so I won't repeat it here. We can find a bounded linear function L such that L of y is equal to 0 for all y in y, and L different from 0. So Lx different from 0. So we start with this, and this is a bounded L, a bounded linear functional defined in this space. And now you use Hahn-Banach theorem to extend this bounded linear functional to the whole space, and what you get at the end is that there exists a bounded linear functional, so let me represent it by L again, such that, well, so this is a bounded linear functional, so an element of x prime, such that L of y is equal to 0 for all y. So since Zn belongs to y, this means that Lzn is equal to 0 for all n, and L is different from 0. L is different from 0 because L of x is different from 0. And now by dividing L by its norm, I can assume without loss of generality that the norm of L is equal to 1. Right? If the norm of L is not equal to 1, you take the bounded linear functional you defined. Its norm is different from 0 because L is different from 0. You divide this bounded linear function by its norm, you get a new bounded linear functional which vanish at Zn, which is different from 0, and whose norm is equal to 1. So there is no loss of generality by assuming that the norm of L is equal to 1. We want to get a contradiction, and the contradiction will be obtained by obtaining a contradiction on the norm of Ln. So I want to obtain now a lower bound and an upper bound for the norm of Ln. So we'll start by a lower bound, sorry. So the lower bound will be obtained for the linear functional which approximates L. So fix an epsilon positive. Since this family is dense, you know that there exists an n such that the norm of Ln minus n is bounded by epsilon. Right? This comes from the density of this family Ln. Now I want to get a lower bound for Ln. So I'll just say that, consider the norm of Ln. Well, by the triangle inequality, this norm is certainly less than or larger than the norm of L minus L minus Ln. Okay, because the norm of L is bounded by the norm of Ln plus the norm of L minus Ln. The norm of L is equal to 1. The norm of Ln minus L is bounded by epsilon, so we get a minus sign here, so this is larger or equal than 1 minus epsilon. So this gives us a lower bound on the norm of Ln. Now I want to get an upper bound. To get the upper bound, we'll use the property of Zn. So the norm of Ln is bounded by 2 times Ln Zn. Well, L of Zn it's equal to 0. So this is 2 times. I can add and subtract L of Zn. Now I can use the bound that, well, this is actually Ln minus L applied at Zn. And by the definition of the norm, this is of Ln minus L. This is bounded by 2 times the norm of Ln minus L times the norm of Zn. Right? Because Ln minus L is the supremum. Well, but the Zn were chosen so that the norm is equal to 1. So actually, this is equal to 2 times the norm of Ln minus L. And the norm of Ln minus L is bounded by epsilon. So this is bounded by 2 times epsilon. So on the one hand, we have that the norm of Ln is bounded by 2 epsilon. On the other hand, we have that the norm of Ln is bounded below by 1 minus epsilon. So from that, we get that 1 minus epsilon is smaller than 2 epsilon. So that 3 epsilon is larger than 1. So if we take epsilon strictly smaller than 1/3, we get a contradiction. This can't be true. And since this can't be true, we conclude that the closed linear span of Zn is exactly equal to x, as I claimed. So let's conclude. Well, we proved up to now that the closed linear span of Zn, of this family you constructed, is equal to x. So remember, the closed linear span of this family is the closure of all finite linear combinations of Zn. So this space is actually equal to the space of all sums from 1, let's say, to m of alpha j, z, and j, in which we are taking here m larger than 1, and we are taking alpha 1, alpha m in R. And we take the closure of that space. Well, what I claim is that it's clear that this space coincides with the closure of the same space where instead of taking these scalars in R, we take them in Q as rational numbers. So any element of such a type of element can be approximated by an element here in which the scalars are taking in the rational. So this means that the closure of that space contained this space without the closure, and therefore that the closure contains also the closure because, well, this is a closed space. And so that proves that this inequality and the other inequality is obvious. So these two spaces are equal. Now, it's clear that this set is countable, and therefore we have that x, which is equal to that space, it's equal to that space. Well, we obtained a countable space whose closure is equal to x, which means a countable space which is dense in x, and that completes the proof of the theorem. Just a remark on the previous theorem is that, well, it gives us another proof of the fact that the space of continuous function in -1, 1 is not reflexive. All right, because, well, again, we will proceed by contradiction. So suppose they were equal. Well, we know that this space, it's separable. It is easy to construct a countable dense family of continuous functions. So if those two spaces are equal, that would mean that C double prime it's separable, and by the previous theorem, that will say that C prime -1, 1 is separable. So let's show that C prime is not separable. So my claim is that C prime -1, 1 is not separable. And let's define a family. So let's consider the following, maybe to keep my notation LT. So LT of x is, so x it's a continuous function. I I fix t in minus 1, 1. And I want to define a bounded linear function L indexed by t. Well, Lt at x, it's simply x computed at t. So I leave it to you to show that Lt, it's a bounded linear functional. That's pretty clear. And what I claim is that if you take s different from t, then the norm of Lt minus Ls, it's equal to 2. This for any s different from t. And why? Well, first, as usual, we'll get a lower bound and then an upper bound. So let's start with the upper bound. So Ls Lt at x. So this is always, well, this is equal to xt minus xs. And if I take x, so x is a continuous function whose norm it's equal, whose an infinity norm it's equal to 1. So this means that x it's bounded by 1. So this is bounded by 2. And this holds for all functions x with L infinity norm equal to 1. So if I take the supremum here, I get that the supremum is bounded by 2. And therefore, this proves that Lt minus Ls has norm less or equal than 2. So now let's prove the lower bound. So Lt minus Ls, it's the supremum, so that's larger or equal than Lt x minus Ls of x for any continuous function bounded by 1. So if I have here s and t, let's consider a function x which takes the value 1 at s and minus 1 at t, any continuous function. So we can think of this function. So Ltx minus Lx, it's by definition xt minus xs. And this difference, well, it's 1 minus minus 1, so this is 2. And so we get the lower bound. So this proves that indeed what I claimed, which is that Lt minus Ls, the norm of that, it's equal to 2. So we have a family, which is an uncountable family, which has the following property. If you take any two distinct elements, the norm of the difference, it's equal to 2. And we have seen in the previous example that if this is the case, that's the set, X, the set of all such elements. In our case, the set of all bounded linear functionals on minus 1, 1 cannot have a dense and countable subset, because, well, you won't be able to approximate all these bounded linear functional by this dense and countable set. Otherwise, you will have a bijection between countable and uncountable sets. So here is the last result of this lecture. It's again a theorem, and it says the following: let X be a normed linear space which is reflexive. So let's assume that the scalars are the real numbers, because we will use Banach, and let's consider Y a closed, so Y it's closed linear subset. And what I claim is that Y it's reflexive, which means that Y double prime is equal to Y. And so let's start the proof by writing down what we need to prove. So we need to show that W double prime is equal to Y, which means that if I have L, which is a linear functional from y prime to R, bounded linear functional. So this means L, capital L, an element of y double prime. Then what I need to prove is that there exists z in y such that L of L, it's actually equal to Lz of L, and this is by definition Lz for all L. So I need to find a z such that for all L in y prime, I have that L of L is actually equal to L of z. So let me say again, what I need to prove is that you fix an element of y double prime, which means the bounded linear functional from y prime to R. And what I need to show is that then I can find an element of y such that whatever element of y prime, which means whatever bounded linear functional defined on y, L of L, so that given L, it's equal to Lz. This is what we need to prove. And what we know is something about x, because we know that x, it's reflexive. So what we will need to do is to, starting from these functionals which are defined on y prime, get a functional which are defined in x prime, and then use the fact that x is reflexive. So let me just, so we have here two spaces, x and y. We have then x prime, y prime, and x double prime. So let me fix notation, because notation will be slightly heavy in this proof. So points in x and y will be represented by x, y, z. Then points in x prime, y prime will be represented by L, sometimes m, and here capital L. So now if I have a functional L, which is defined on x, which is a bounded linear functional, and I won't repeat that, every time I write either small l or capital L, I always, or m, meaning bounded linear functionals, just the space is changing in which they are defined. Well, if I have a L defined on x, so L, an element of x prime, I will represent by Ly its restriction to y. So Ly, it's now a bounded linear functional defined on y, which coincide with L on y. So Ly of y will be just equal to L of y. And this allows me to go from x prime to an element Ly of y prime. And it's also clear that the norm of this Ly is bounded by the norm of L. Right, the norm of Ly involves a supremum over elements y in y, and this will be bounded by a supremum over elements in x. So keep in mind that inequality. So this is a way in which you can go from an element in x prime to an element in y prime. But now I can do also the opposite. So if I now have, say, a functional m which is defined in y, which is bounded, so m, it's an element of y prime, I can extend it by using Han-Banach to an element m0, which is now in x. The problem here is that this extension is not unique. So if you started from an element in y prime, you can always use Han-Banach to get an element m0, which is in x prime. And Han-Banach will tell you that the norm of m0 is equal to the norm of m, but there is a problem here is that, well, this extension is not unique, so you don't know exactly what you're talking about when you say that your extension. You just need that there exists one. So these will be the building blocks of the proof of this result. So I just copy here what we need to prove. We need to show that for all L defined in y prime to R, I can find a z in y, such that for all L in y prime, L of L is equal to L of z. So let's start with L defined in y prime. So L, an element of y prime prime. And I want to define L0 from x prime to R. So let's take m in x prime. So this means that m is a functional bounded linear function from x to R. I have to define L0 of m, but for that I need to use L, so I need to transform this bounded linear function from x as a bounded linear function in y. We have seen how to do that. We've seen that its restriction to y, which is well defined and represented by mu of y. So this is an element of y prime. And so I will define, let me write it here, L0 of m as L of my. So this is my definition of L0, and I need to show, and this is my first claim, is that L0, it's a bounded linear function. So I need to show that it's linear. Well, let me just show that the sum is linear to the sum, to the addition. So let's consider L0 of L plus m. By definition, this is L of L plus m, the restriction to y. So I'm taking the bounded linear function of L plus m, and I'm restricting this sum to y. But this is, of course, equal to L. Well, this sum, it's equal to the sum of Ly, the restriction of L to y, plus the restriction of m to y. Now L is linear, so this is equal to Ly plus L of my. And by definition, this is L0 of L plus L0 of m. And you can also, by the same line of argument, show that L0 it's also linear by multiplication by scalars. So it's clear that it's linear. So now let's check that it's bounded. So to prove that it's bounded, we need to estimate L0 of m. Well, by definition, this is L of my. By definition of the norm of L, this is bounded by the norm of L times the norm of my. And here, just to remember that my, it's a linear function defined on y. So this is the norm in y. And we have seen that this norm, it's bounded by the norm of m. And from that, we get that the norm of L0, it's bounded by the norm of L. All right, so L0 defined through this formula, it's indeed an element of x prime, x double prime, right? It's a bounded linear function defined on x prime. So L0, it's an element of x double prime, and therefore we now can use the fact that X is reflexive to say that actually there exists an element Z in X such that L0 of M it's equal to mz for all m in X prime. Okay, so now I will erase everything and I will start from this definition. I'll keep this fact and I will continue the proof. Now, just an observation. Consider L and M defined in elements of y prime, or maybe L, just L defined as an element of y prime. So L, it's a bounded linear function all defined on y. As we have seen, we can extend by using Han-Banach L to the whole space. So let me represent by L hat an extension. There are many extensions, but let's consider one of them. And this extension, it's built in such a way that its norm, it's equal to the norm of L. So we started from a bounded linear function defined on y, and we obtained one which is defined on x. And as we have seen, well, this extension is not unique. So let's denote it by L hat 1 and L hat 2, two possible extensions. Now I want to apply L0 to both extensions, to one of them. Well, but since L hat 1 and L hat 2 are extension, this means that if I project them on y, I get the same bounded linear function, which is L. So this means that now when I compute L0 applied at L1 hat, say, well, this by definition, it's L applied to L hat 1 restricted to y. So this is L1. We extended L1 to the whole space X. And after extending, we restricted it to y. Well, but this is exactly L of L, right? Because the restriction to y coincides with the original one. And therefore, if I repeat the same computation for the second one, what I get is that the value, it's the same, whatever the extension. So whatever, if you start from one bounded linear functional defined on y, the value of L0 at whatever extension is the same. So we'll use this fact now. So keep that in mind. And to prove the following claim, I claim that this z, which appeared in this identity, belongs to y. So my claim is that z belongs to y. So to prove that z belongs to y, we'll proceed by contradiction. So assume it doesn't belong to y, and we'll get a contradiction. So assume that z doesn't belong to y. And here we are going to use that y, it's a closed linear subspace. If y it's a closed linear subspace, I can construct a linear function of m on the space generated by y and z. So the space of alpha z plus y, where alpha it's a real number and y it's an element of y, such that well, m is of alpha z plus y. So what I want is that, well, let me write it in the following way. M vanish at y. So m of y, it's equal to 0 for all y. But m of z, well, it's different from 0. So we've seen that because y it's a closed linear space, that we can define such a bounded linear functional. We've proved that many times. So since y it's closed, we can define a bounded linear functional which vanish on y and which doesn't vanish at that point z, which doesn't belong to this closed subspace y. So this is possible. And now let's see what we have. Well, let me call m hat an extension of m to x. So here m is defined on subspace of x. Well, let's use Han-Banach to obtain an extension of m to x. Well, on the one hand, now let's apply L0. L0, it's our bounded linear functional defined on x prime. Right? So M0, it's an extension, so m hat, it's an element of x prime. And let me apply L, which is L0, which is an element of x double prime, to m star. Let me apply L0, which is an element of x double prime, to m hat. Well, by definition, this is equal to L, the restriction of m hat to y. So let me represent in this way L, the restriction to y of m hat. And we know that the restriction to m to y, well, coincides with m because m hat is an extension of m. And m at y vanish, so the restriction of m hat to y is 0. So this is equal to L of 0, and this is 0. Right? This restriction is just the bounded linear function, which is equal to 0 at every element. So it's the element 0 of y prime, and therefore this is 0. Well, on the other hand, we know that this is our point z. We know that L0 of m hat, it's, so by this fact that we know already, that there exists a z in x for which this is equal to mz, L0 of m hat, it's equal to m hat z. M hat z, well, it's an extension, so this is m at z, and we constructed m in such a way that this is different from 0. So we get a contradiction, because on the one hand, we get that L0 of m hat, it's different from 0, and on the other hand, we get that L0 of m hat, it's equal to 0. So this proves that this point z has to belong to y. So let me summarize what we did already. Well, we defined this functional L0, so we fixed a bounded linear functional L in y double prime. With that L, we defined this L0, and we proved that, well, L0 is a bounded linear function, but more than that, we proved that there exists a z, which is actually in y, for which this identity holds for all m in x prime. Now we are ready to conclude. What I claim is that L of m, it's equal to m of z for all m in y prime. So let's take m in y prime. Let's consider its extension. Let's write m hat as its extension to x prime. whatever we have proved, that whatever the extension, so if you take an extension 1 or an extension 2, so whatever the extension, the value of L0 at both of them are the same. So we started from M. We consider M hat an extension of M to the whole space of X. We have that L of M, it's equal to L0 of M of its extension, right? Because this identity has to be understood that you take M, you consider its extension. Now you compute L0 of the M extension. By definition, it's L of the restriction. By the restriction to Y of M hat, it's M. So we have this identity. So we prove that this is equal to that. Now I know by the property of L0, because X is reflexive, that this is equal to M hat of Z. But Z, it's a point in Y, and M hat, it's an extension of M, so they coincide at Y, so this is equal to MZ. And this proves that, indeed, whatever M in Y prime, L of M is equal to M of Z, where Z is this point which was obtained from the fact that X is reflexive, and that completes the proof of this theorem.